Here. We're going to continue on with chapter 16, and then we'll go off to 17 maybe as well. Okay, so in 16, we started talking about acids and bases, and a reminder that basically an acid is something that will produce H plus or H3O plus, basically ions in solution. And when we talk about H plus and H3O plus, they are used pretty much interchangeably when we're doing acid and bases, both in formulas and also in actual equations or reactions that you write. A base, on the other hand, again, is something that's able to produce hydroxide or OH minus in solution, make something a base. We talked about sort of general definitions of acid and bases, and one that most people think about, which is the Bronsted-Lowry definition of an acid or a base. Bronsted acid is a proton donor. So again, it is something that gives away not just an H, but an H plus. So our Bronsted acid, again, is a proton donor, while our base is a proton acceptor. And as we talked about last time, it's really important. It's not just, again, the H sort of being transferred, but it is that plus charge that goes with it. So again, the charge is affected as somebody sort of loses an H plus or gains an H plus in that sort of process. The result of that is that we create these things which are referred to as conjugate acids and conjugate bases. And these are partners to our acid and bases. So as we talked about sort of last time as well, the regular acids and the bases are usually found on the reactant side of the arrow. Your conjugate partners, conjugate acid and conjugate base, are found on the product side. And again, the relationship is if it's an acid on the left-hand side, its partner is the conjugate base on the other side, while if we have a base on one side, its partner on the other side is the conjugate acid. The important thing is that difference right here. It is just one H plus difference. So that is the only difference that there can be in order for these things to be related to each other. So if it's more than one H plus, then they are not partners. And if it is one H plus, they are again partners. The other relationship that we also talked about in terms of those two things is that there's sort of an opposite relationship. And what that means is if it comes from a strong acid or strong base, its conjugate partner on the other side will be relatively weak, and vice versa. If it comes from a weak acid or a weak base, its partner on the other side will be relatively strong, the conjugate sort of partner to that. We talked about some strong acids, which is a good way for us to just sort of know if it is strong acids or not. But things like hydrochloric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydriodic acid, those are all sort of strong acids. For the most part, things in this class would probably be strong acids. Weak acids or weak bases, in terms of calculation part of, say, calculating the pH or something like that, it's a lot more involved, and you don't really get into that until you get to Chem 1B in that sense. But so if you see it, in the sense of calculating something like pH, is probably going to be a strong acid or base in this class. Also, strong bases typically do have hydroxide or that OH minus in the actual solution. So you typically are in the actual formula. So something like sodium hydroxide, potassium hydroxide, calcium hydroxide, or strontium hydroxide, those guys kind of from group 1 and 2 on the periodic table that has OH in the actual formula. A lot of times those guys are definitely strong bases. That's what alkaline means. If somebody says make it alkaline, it means to make it basic. And a lot of our strong bases come from our alkaline metals or alkaline earth metals from our periodic table. We also talked about a relationship which is known as Kw, and that is Kw is the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to the minus 14. So this is the equilibrium constant for water, and it allows us to figure out, the acid part of the solution and the base part of the solution. So the little brackets means concentration, usually means molarity, which is moles per liter. And if we know, say, the H plus part of the concentration, we could figure out the OH minus part by solving for 1 times 10 to minus 14 divided by the H plus, and vice versa is really the same calculation. And we could compare these two sort of values that we get, the concentration of H plus versus the concentration of OH minus. And if the H plus is larger than the OH minus concentration, then it's going to be acidic. If the OH minus is larger than the H plus concentration, it will be basic. If they are equal to each other, that means they both have a concentration of 1 times 10 to the minus 7, which means that they have a pH of 7 and they're going to be neutral. Also important to make sure we use our exponent button definitely in this chapter. So otherwise you will find yourself pretty far off the right answers and stuff like that. We then, I think, sort of finished up talking about the pH scale. And the pH is equal to minus the log of the H plus. Yeah, so to answer your question, in terms of Ks, so Ks are equilibrium constants. So the question was, will we have any other Ks besides Kw in this class? And the answer is probably not in this class. So Kw is one that is used a lot, but Kw is really just K, as we'll talk about actually in the next chapter 17. And K is the equilibrium constant. And typically equilibrium constants in the context of sort of acids and bases, they're used for weak acids and weak bases when you have to do some type of calculation. And we really don't do calculations involving weak acids or weak bases. Definitely if you take, like I said before, 1B, you'll do a lot of calculations involving Ks. You'll do a lot of things with weak acids and weak bases and stuff like that. So yes, later on, but probably not in this class in terms of anything that you would have to calculate in sort of the context of acids and bases other than using Kw. So we were talking about sort of the pH scale, and the pH scale runs from 0 to 7 to 14. Below 7 is acidic, above 7 is basic. And as we just talked about, if those concentrations are equal to each other, it will give you a pH of 7, which is neutral. To calculate the pH, it's minus the log of the H plus concentration. And we talked about calculators as well. So again, if you have a display calculator, you're going to punch it in exactly the way you find it. So you go minus the log of the H plus concentration, making sure you probably use your exponent button. If you have a non-display calculator, you need to kind of go backwards on those formulas. So usually you need to start with the number, hit log, and then make it negative. And again, if you're not sure which type of calculator you have, you could hit log. And again, if it says log, it's a display calculator, and you could just do all these formulas just the way they're written. If you hit log and it says error, then you need to do this formula. And pretty much all the rest of them we're going to talk about kind of backwards and kind of work backwards in terms of it. Last sort of thing that we also talk about is that relationship between H plus and OH minus. So as one goes up, the other goes down. So it's sort of an opposite relationship between those. And the greater the amount of H plus, the actual lower the pH it would be, and vice versa. The greater amount of OH minus, the higher the pH would be. So 7 in terms of the pH scale, sort of your middle point. As you go towards 14, you're becoming more basic. As you go from 7 towards 0, you're becoming more acidic. Any questions on any of that stuff? I think we talked about last time there. Okay. So I think we saw it. And again, here's a pH scale. As you can see, runs from 0 to 14. And some things that we normally sort of look about. We got sodium hydroxide here, which is a strong base, so upwards in the 14 range in terms of this pH, which makes sense. We have some HCl, which is obviously a strong acid, so that is on the lower end there, towards 0. We actually have pure water, which is 7. We have things like vinegar, lemon, which are acids. We also have ammonia, which is cleaner, as we talked about as well. A lot of sort of cleaners like drain cleaner, Drano, that type of stuff. That's all bases and stuff like that. To be honest with you, if you sort of had water that wasn't, say, pure water, or water that you kind of maybe put in a beaker and let sit around for a while out in the open air, the pH would probably be like in this range here, believe it or not. And that's because as water sort of sits around in the air, kind of picks up some carbon dioxide and makes basically carbonic acid. That's going to increase the H plus concentration a little bit and actually bring down the pH. So actually sort of a lot of times people are surprised. They kind of take tap water or just water, or they leave water out for a while. They're very surprised. It's not necessarily 7. A lot of times it's a little bit more acidic, again, because it picks up that CO2 and kind of increases the H plus concentration a little bit, bringing down the pH. So a lot of times in experiments years ago, they don't do it too much at places, but where we do titration experiments like we were doing, a lot of times they would have you boil the water. And when you would boil the water before you did the titration, what that does is it removes a lot of the CO2 and brings water back up to, sort of neutral. So it doesn't affect your titration all that much. It's usually not a big issue, but sometimes people will sort of do that. HCl. Remember, HCl is one of those strong acids, which means when we do have HCl in solution, it's going to 100% break apart into H plus and Cl minus. And because we 100% have pretty much these guys on our product side, we know that in terms of pH, it is the H plus that is the most important, and it is a 1-to-1 relationship between those two. So if the whole thing has a concentration of 0.015, the H plus would also have a concentration of 0.015. And that's really all we need for our pH calculation. So the pH is equal to minus the log of the H plus. And that means we would put in there minus the log of 0.015. And that's going to give us on our calculator an answer of 1.823908741. That clearly is way too many numbers. So this brings us to what else we talked about last time, which is significant figures and sort of pH. So when we go for a pH value from a concentration, the number of significant figures in our concentration, which in this case is 2 significant figures, tells us not how many significant figures in our pH, but how many decimal places we should have, which would be 2 decimal places. So we should end up with 1.82 as our answer. So remember that when we go from concentration to pH, we're going from significant figures to decimal places, and also backwards as well. So if we go from sort of pH back to H plus concentration, we also want to do decimals to significant figures. First off, any questions on that calculation there? This also would tell us that it is 1.82, which is less than 7. So it would be acidic in this case, which would make sense since this is an acid. Any questions on that calculation? So while we're talking about it, let's talk about, kind of going the other way. So for example, if we have the pH given to us, from the pH, it actually tells us what we could get. We could actually get the H plus concentration directly from the pH value that's given to us. And to do that, we're basically going to take the inverse log of the minus pH. So if you're given the pH value and you want to calculate the H plus concentration, you're going to do the inverse log of the minus pH. On most people's calculators, when you hit the inverse log, that's a 10 and a caret usually pops up, and like a minus pH. Again, inverse log is usually top left of your calculator. You got like the second button, the shift button, right? And then obviously above usually your log button is where you find that 10 to the X type of thing. So that's usually where most people have been using as scientific notation, which you shouldn't. This is actually what you should be using it for here. So usually top left there, second or shift, and then hit the log button, should usually pop up a 10 and a caret, and then make sure you make it negative. Otherwise you will get the wrong answer there, the pH value. So if we're going sort of in this direction here, so for example, we could just test it here. If we wanted to do this, the pH here was 1.82. So if we did the inverse log of the minus 1.82, again on your calculator, it will look something like this when you punch it in correctly. And hopefully we should get, obviously, what we started with there, which is 0.015. So again, if we do this on our calculator, it spits out 0.015135612. So going backwards here, since we started with the pH value at 0.82, that's 2 decimal places. We would go not to 2 decimal places, but to 2 significant figures here, which gets us back to our original number of 0.015 molar. So again, you want to kind of follow that rule no matter sort of which way you're going, kind of forward or backwards on that calculation. Again, sig figs to decimal places going one way, our decimal places back to significant figures going the other way. Any questions on that? And again, this is why it's really important in this chapter for sure to make sure that you are using your exponent button, because if you are still doing exponents sort of this way or using the multiplication button, as you start doing these logs, these inverse logs, you are going to find yourself pretty far off from the right answer. Any questions on either one of those there? Okay, so why don't you try another one here just to make sure calculator is all working. The pH of a solution is 5.85. What is the H plus concentration? Would be the inverse log of the minus pH. So again, if we do that and kind of hit inverse log, usually will pop up a 10 and a caret. We want to make sure that we do make it negative 5.85. And if we do that, it looks like you get something like 1.412537 times 10 to the minus 6. Again, if you're not in scientific notation, it probably just punch out all the zeros there, 0.00001413 on your calculator. Again, going backwards here, we have 2 decimal places here for our pH, which means we should end up with not 2 decimal places, but 2 significant figures in our answer. So we should end up with 1.4 times 10 to the minus 6. And it is molar, so you do want to put the M there for it. And that would give us our H plus concentration. Again, in this case, going from decimal places to significant figures, so going backwards in this case. Any questions first off on that part of the answer? Now that we have the H plus concentration, we actually can use Kw that we talked about last time and use that to figure out our OH minus concentration. And again, it is basically the same calculation regardless of which one you have. So it'll be 1 times 10 to the minus 14 divided by, in this case, our H plus concentration. So we would have 1 times 10 to the minus 14 divided by 1.4 times 10 to the minus 6. Again, you definitely want to use your exponent button. So 1 exponent button negative 14 divided by 1.4 exponent button negative 6, going to get us something like 7.1 times 10 to the minus 9. Also going to be molarity because it's a concentration. And this would be our hydroxide concentration. Any questions on that there? Now we can compare both of these values if you want, but we don't really need to because the pH was given to us. So they both should tell us the same thing. pH is less than 7 here, so it should be acidic as it's less than 7. And that means that our H plus concentration should be larger than our OH minus, which it is. Again, 10 to the minus 6 is a larger number than 10 to the minus 9. Any questions on any aspect of that calculation? Why we did any of it, or any of that type of stuff? Okay. So again, really important. Most people really screw up with not being able to sort of punch these things in correctly into their calculator. So, you know, make sure, again, you use your exponent buttons and you sort of punch things in the right order. The other common mistake that people make as well is they oftentimes will try to use the subtract button instead of the negative button. So make sure you are using your negative button. Any questions? Okay. So that's pH, and that's how you could get the H plus from the pH value. There's also a very similar scale to the pH that is sometimes used, and sometimes it's kind of helpful as well. And that's what is known as the POH. So there is a nice relationship that you could calculate what is known as the POH. And the POH is minus the log of the OH minus concentration. Again, the name really does tell you what you need. POH means you need OH minus concentration. If you're given the POH without having to do a lot of other calculations. So these guys here are really important sort of calculations. They help you a lot. One very important thing, though, is the POH scale actually runs opposite of the pH scale. So what that means is if you have a low pH, you have a high POH, and vice versa. If you have a high pH, you have a low POH. So most people remember the pH scale, and that's what they have in their head, and that's what you should look at when you're trying to determine if it's acidic, basic, or neutral. And again, that's because the POH is opposite. So, you know, if you look at the POH scale, it goes from 0 to 7 to 14, except that this is basic in this area. This is acidic, and then this is still neutral. So because most people have the pH scale in their head, you should always look at the pH to determine acidic, basic, or neutral. And this is also where people mess up on, as we also talked about last time. This is where people will sometimes give multiple answers when they're asked that question. Is this solution acidic, basic, or neutral? They'll go, hey, the pH is above 7, so it's basic. And then they'll go, oh, the POH was lower than 7, so it's acidic. And they'll say the same solution is both acidic and basic at the same time. So again, it cannot be that. It can only be one of those answers. Either it's acidic, basic, or neutral. Always, I highly recommend always look at the pH value to determine that. Any questions on that? So why don't you try this? What is the pH of the solution while we're at it? What is the POH and what is the OH minus? And is it acidic, basic, or neutral? So give it a go, see what you come up with. pH, so our pH is going to be minus the log of 4.8 times 10 to the minus 7. Again, make sure you use the exponent button. And if we do that, that's 4.8 exponent button minus 7, going to give us a pH of 6.32 in this case. Again, we had 2 significant figures here, going to give us 2 decimal places here. Once we have the pH, we could actually get the POH pretty quickly because the pH plus the POH is equal to 14, which means that the POH would be 14 minus our 6.32, which is going to get us, looks like 7.68 as the POH. And really at this point, I do have 2 options as to how I could get to the OH minus. I could use KW and our H plus concentration, but I'm going to use my POH since we just talked about that. So the OH minus would equal the inverse log of the minus POH. And that would get us, again, usually a 10 and a caret when you punch the inverse log in. We want to make it negative. And again, we want to use our POH value, which is the 7.68. And that will get us, I believe, something like 2.1 times 10 to the minus 8 molar. Again, going backwards from our POH value to our concentration value, we have 2 decimal places. Gives us, again, 2 significant figures going this direction backwards. Again, if you use kW, which is 1 times 10 to the minus 14 divided by 4.8 times 10 to the minus 7, should also give you the same answer. So it's perfectly fine. Whichever way you want to do it, it should give you the same sort of answer. First off, any questions on any of the numbers that we got there?
Yeah, wouldn't it be 1 decimal point? Because like we're starting the log with 4.8, so why would it be 2 decimal points?
Are you talking about this number right here, the pH?
Mm-hmm.
Yeah. So our original concentration is in scientific notation. So this has 2 significant figures.
Okay, yeah, okay, I was thinking the opposite.
Yeah. So it's sometimes confusing for people because they go sig figs, or decimal, but
Mm-hmm.
it's actually significant figures in concentration to decimal places there in the
Okay.
pH or the POH value as well. So if we go the opposite way at the end, that's why we looked here when we had the 2 decimal places. That got us back to 2 significant figures in the concentration going backwards. Other questions? Okay, so we also want to know, is it acidic, basic, or neutral? And again, this is a situation where people sometimes run into trouble because they have 2 of these numbers here. But really, I would always look at the pH value. And when we look at the pH value, we see it's less than 7. So that means it should be acidic because of that. Again, it would not be acidic and basic because of these numbers. Again, just the pH value. Other questions on that? Okay, so hopefully you're getting the hang of the calculator and sort of punching them in correctly. That's half the battle usually on these type of problems. So we talked a little bit about bases, but just to reiterate, strong bases, again, usually will contain hydroxide, and you will have it in the actual formula. So things like our sodium hydroxide and our potassium hydroxide here. Again, calcium hydroxide. So like I mentioned maybe the other day as well, if you kind of go to group 2 on the 1 and 2 on the periodic table, you have like sodium, potassium, you hang a right over there, the calcium, strontium. So a lot of your strong bases are like in this region on the periodic table in group 1 and 2 that actually does have hydroxide in the actual formula. And because it's a strong base, it's a strong electrolyte. So as we've talked about before, 100% of it is going to break apart into these ions. So again, it's a 1-to-1 relationship in this particular case, say between sodium hydroxide and the OH minus concentration. So you essentially do have the OH minus concentration given to you if you are given sort of the concentration of each of those things. And again, you would have your same concentration. But as we've talked about, I think previously as well, if we had something like calcium hydroxide, when it does break apart, you do have to take into account that adjustment that happens with how many hydroxides that you do get. So as you can see here, if this is 2.25 molar, this is no longer a 1-to-1 relationship. It's a 1-to-2 relationship. So like we talked about with ions and concentration, basically 2 times that 2.25 molar, going to give you your 5.50 molar. And that's what you would use to calculate something like the POH value, would be this one here. So again, some strong bases do, when they break apart, like we see here, is calcium hydroxide into a couple of hydroxide. So you do have to double the concentration. You don't have to do that, obviously, with the sodium hydroxide or the potassium hydroxide. Again, it's a 1-to-1 relationship in that particular case. So sometimes they don't in acid and base problems. Just a lot of times they will just give you like a generic, hey, the H plus concentration is this, or the OH minus concentration is this. But sometimes they will give you formulas. So they may give you something like HCl, they may give you something like KOH. And like I mentioned earlier today as well, pretty much you could assume that if it's a question where they're asking you for the pH of something and they give you an actual formula like HCl, KOH, you could probably safely assume that those guys are going to either be strong acids or strong bases, because as I mentioned earlier, it's a much different calculation if they're weak acids and weak bases to calculate the pH. And that's like a whole chapter in Chem 1B that you will take probably later on and stuff like that. So for our purposes in this class, probably almost a safe bet if you're actually given a formula of an acid or base and you're not 100% sure if it's strong or weak, it's probably going to be on the strong side, because again, the weak acid or base calculation is much, much different than just putting it into the formulas. Any questions on that? Again, not all bases will have hydroxide in it, and a lot of weak bases do not have hydroxide in it, but they're able to produce hydroxide. So a very common example is ammonia. Ammonia is a weak base. It does not have any OH in it, but when it reacts with water, it actually accepts the H plus from water, and by doing so, it generates some OH minus. It's a weak electrolyte, as we can see here with our arrows heading in both directions. Which means, you know, it mainly stays over here, but it does produce a little of these guys. And because it's still able to produce a little bit of OH minus in the solution, it's still really considered a base because of that. Again, it's not going to be able to produce anywhere near the amount of OH minus as, say, something like sodium hydroxide. So if you had like, say, something like sodium fluoride, it breaks apart into sodium and fluoride. It's actually the fluoride ion that reacts with water and accepts the H plus and makes HF and OH minus. And it's actually the F minus part of that that actually is the base part. And it's a weak base for the same reason. Again, it's only going to produce a little bit of this. So if you had like NaF in solution and you dump some sodium hydroxide in there, the sodium hydroxide is going to be the major contributor to OH minus in that solution, because pretty much all it needs to do is go for a swim and it's going to produce a lot of OH minus very quickly. The F minus got to go hunt down some water, do a little reaction, and produce some OH minus. So those strong bases are definitely always much, much stronger than any type of weak base. Now, as we sort of talked about the POH and the is minus the log of the OH minus, it does describe sort of the OH minus concentration. I'm going to assume you can still hear me, I hope. Yes, because everything just froze again on my side. Yeah, everybody could hear me. Somebody nod that I could see video. Yes. Yeah. Okay, so I'll just continue on then. I might just be frozen, I suppose, in my picture and stuff like that. But the POH is, again, minus the log of the OH minus, and it does describe the OH minus concentration. So as the OH minus concentration goes up, remember that it's an opposite relationship. The H plus concentration goes down. So they do run opposites of each other. And the greater the amount of OH minus, we're going to have a more basic pH. The less of it, we'll have a more acidic pH. In terms of significant figures and calculations, it really does work the same way. We take the number of decimal places is going to be how many significant figures there was in the OH minus concentration. So it works the same way going backwards and forwards. So as we see here, if we started with a POH of 3.45, it has 2 decimal places. If we were taking that back to the OH minus concentration, which we would do the exact same calculation as the pH one, we would end up with 10 to the minus 3.45. And again, just to make sure here, if we put that into, we end up with something like 3.5481, times 10 to the minus 4. 2 decimal places here should round our number to here, and we would end up with 3.5 times 10 to the minus 4 molar. Again, going from POH to concentration, we're going from decimal places to significant figures. So kind of that back and forth. Any questions on that there? So as I mentioned earlier, again, the pH and the POH are ran opposites of each other in terms of their scale. And if we have a acidic pH, that means we would have kind of a higher pOH. So it's always important to look at just the pH value when you're doing that. Again, most people only have the pH in their head in terms of the scale. They do run opposites of each other. Again, as I mentioned, they cannot be all. I've never really seen anybody do all three, but sometimes people very commonly will go, again, it's acidic and basic at the same time. So only one answer when you're asked that. Don't give all three, which again, I haven't really seen. All right, so why don't you take a moment here and do the pOH of this solution, which has an OH minus, and why don't we do the rest of it as well? Let's do the pH. Why don't we just make sure everything's still working? H plus, OH minus, and is it acidic, basic, or neutral? Not OH minus since they gave you that. So let's just do those guys. The pH formula, which again is pOH is equal to minus the log of our OH minus. So we're going to do minus the log of 2.08 times 10 to the minus 5. Again, we want to make sure that we do use our exponent button, and that's going to be minus the log of 2.08 to the minus 5. And again, that is going to get us a pOH of 4.68, actually 2 in this case. And you may be saying, why so many decimal places? So in this case, we actually have 3 significant figures here, which means technically speaking, we should end up with 3 decimal places in this particular case. Any questions on that there? Now that we have the pOH, we can easily get the pH because the pH and the pOH is equal to 14. And that would get us the pH is 14 minus 4.682. And if we subtract 14 from it, we'll go with 9.318 as our pH value. And again, we have multiple ways we could get to the H plus. We could use KW like we did before. We could also just use our pH value that we just got. So why don't we try it that way? So our H plus will equal the inverse log of the minus pH, which will give us a 10 and a caret minus 9.318. And that's going to get us 4.81 times 10 to the minus 10. Again, molar would be the units we want. Here, 3 decimal places, 3 significant figures going backwards. And lastly, we have a pH that's 9.318, which means it should be basic. Any questions on where any of the answers came from or how we did any of those guys there? All right, so you can see there's, again, multiple ways you could kind of solve these problems depending on sort of the information given to you. And again, you just want to maybe choose whichever way is easiest or whichever way you're comfortable punching it into your calculator. Again, you could use KW as well if that helps. You could use KW and got the H plus concentration, then went into the pH equation. So there's multiple sort of routes that you could kind of go through as you're going through these guys. Any questions on that? Okay. So we sort of talked about that relationship. There's all of those guys. So let's do this here. Calculate the pOH for each of these. We have an H plus concentration that's 1 times 10 to the minus 4, and an OH minus concentration of 0.04 at that point. So that might be the easiest route. You could also go an alternative route where you use KW to get to the OH minus concentration, and then you could go to the pOH. So again, no matter sort of which route you take, they all should get you really to the same sort of end result. So I'm going to do that first. I'm going to go right into the pH equation, which is minus the log of our H plus, and that'll get you as minus the log of 1 times 10 to the minus 4. It's going to give me a, not that, minus the log of 1 to the minus 4. It's going to give me a pH of 4.00. And now I could use that POH relationship that the POH would be 14 minus the pH. And that would give me 14 minus 4, which should give me a POH of 10 in this particular case. Any questions on that one there? Now, this second one here, we have the OH minus concentration, which means we could go right into our POH. POH is equal to minus the log of the OH minus. It's going to be minus the log of 0.04 molar and minus the log of 0.04, going to give us a POH in this case of 1.40. Again, 2 significant figures here and 2 decimal places here. Same thing here, 2 sig figs, 2 decimal places. Any questions on either of those there? First solution is acidic because the pH is 4. The second solution is basic as the pH is actually 12.6. So this guy would be basic in this case, as is 12.06 pH. Any questions on those two there? Okay. So again here, the pH of a solution is 5.85 like we saw earlier. What is the OH minus? Again, multiple routes you could do this. Since we have the pH, we could use our POH is equal to 14 minus our pH, going to give us 14 minus 5.85. That's going to get us 8.15 as our POH. And from that, again, we could use the OH minus is the inverse log of the minus POH. Going to give us a 10 and a caret, 8.15. Make sure you make it negative. And again, going to get us something like 7.1 times 10 to the minus 9 molar. Again, if you wanted to, you could use KW. From the pH value, you could do this to get to the H plus concentration, and then use KW to get to the OH minus. Again, should end up same spot if you went that direction. Again, you would do H plus 10 to the minus 5.85, and then that will get you your answer of 1.4 times 10 to the minus 6 molar. And then you could use your OH minus 1 times 10 to the minus 14 divided by that number. And again, that should get you to the same answer we got below as well. And again, it's just a preference as to sort of, I'll just connect it this way, which way you want to do it. They all should really get you to the same spot as long as you sort of choose an appropriate pathway. Any questions on how to calculate pH, POH, OH minus, H plus concentrations from pH, POH? Any questions on any of those guys? And again, like I said, majority of people struggle with how to sort of punch it in and sort of what they're actually being asked to solve for. So again, those sort of 4 important equations or so, minus the log of the H plus, POH is minus the log of the OH minus, our pH plus our POH is equal to 14. H plus inverse log of the minus pH, and OH minus is inverse log of the minus POH. So these guys here do give you sort of a lot of ways to solve these guys, along with our KW, which is equal to H plus OH minus 1 times 10 to the minus 14. Any questions on any of that stuff there? Okay, so we're going to then kind of finish up this chapter talking about buffers. And buffers are solutions that basically resist changes to pH. And they resist changes to pH when you add acid or base to them. So again, a reminder that a buffer sometimes is mistakenly thought of as a solution that will basically be neutral. And a buffer doesn't always have to be neutral. It can be an acidic buffer. You can have a basic buffer. You can have a neutral buffer. You could actually make a buffer at any sort of pH that you would like. The only difference is, wherever it is in terms of that pH, it basically will maintain the pH even if you add acid or base to it. So one important aspect of it is what it is made out of. So a buffer is made out of either a weak acid and its conjugate base or a weak base and its conjugate acid. So basically what that means is you have two things that are related to each other by a difference of 1H plus. So both of those things has to be in there. You have to have a weak acid and its conjugate base or a weak base and its conjugate acid in the solution to actually allow a buffer to work really well. You cannot make a buffer out of a strong acid or strong base. And that's because when you have a weak acid or a weak base, what happens is in solution, for example, if this is a weak acid, it will set up an equilibrium where we will produce H3O plus and A minus. And what that will do is, because this is a weak electrolyte, it will keep both of these parts in the solution at the same time. So we'll have the acid part of a buffer and the base part of a buffer. And that allows it really to maintain its pH. So these are some examples of buffers. This is acetic acid and acetate. That's a weak acid and its conjugate base. This is nitrous acid and nitrite, weak acid and its conjugate base. This is HCN and CN minus, weak acid and its conjugate base. You could have something like NH3 with NH4 plus. This is a weak base and its conjugate acid. Again, each of these things are related to each other by just one H plus difference. So how does it actually work? So let's talk about really what happens with a buffer and sort of how it works. Let's say if we added, say, to water, HCl, hydrochloric acid. Hydrochloric acid or water is not a buffer. And if we added that to water, it's going to 100% break apart into H plus and Cl minus. And what happens though is we have just created a lot of free H plus very quickly. And because the H plus concentration went up, we would expect the pH to go down. So we would expect a pretty good jump in the pH at that point because of the difference here in the H plus concentration. We have basically made a lot of H plus very, very quickly. Now, if we added, say, sodium hydroxide to water, it also is going to 100% break apart into sodium ions and hydroxide ions. And what's going to happen here is we're actually going to generate a lot of free OH minus very fast. And remember that if my OH minus concentration goes up, my H plus concentration will go down. And the result of that is my pH will go up. So we would expect a big jump in the pH in this case as it goes from sort of an increase in our OH minus concentration. Now, if we add these same things to a buffer, say a hydrofluoric acid, and fluoride buffer. Again, this is our weak acid. This is the conjugate base. And if we add that HCl to this buffer, what's going to happen is, since HCl is an acid, it will react with the base part of the buffer. And it will react, and we will get HF and Cl minus in this particular case. And what we see is on the product side, we form some HF, which was in the buffer to begin with. So that's not going to affect the pH. We also form Cl minus, which is a neutral salt. It will not affect the pH. But most importantly, what we do not see here is free H plus. So if we look at what happened with HCl and water, we produced a ton of free H plus very quickly. By adding that same HCl to this buffer, we actually do not produce any free H plus. So because the H plus concentration remains relatively constant, the pH will also remain relatively constant because we have not introduced any more free H plus to this solution. Now, if we added our sodium hydroxide to this buffer, sodium hydroxide is a base, it will react with the acid part of the buffer, and we will get water and some sodium fluoride. Same thing here, we produce water, which is not going to screw up the pH. We produce NaF, which is basically this guy, which was part of the buffer to begin with, so it's not going to screw up the pH. The most important thing here is we did not produce any free OH minus. And because OH minus is tied to H plus, the OH minus concentration remains relatively constant. That means that the H plus concentration will remain relatively constant. And that means that the pH will remain relatively constant as well. So basically how a buffer works is, because it has a acid part and a base part that's in the solution to begin with, when you add acid or you add base to that solution, it basically prevents the formation of free H plus or free OH minus. And it's those two things, free H plus or free OH minus, that really will screw up the pH. And that is because the pH is equal to minus the log of the H plus concentration. So a buffer is able to really keep this H plus concentration relatively constant to where it began. And because it remains relatively constant, the actual pH value will remain relatively constant as well. Any questions on that there?